Welcome back. So we know plates move. We have evidence that they moved in the past. We know that they're moving now. We see the proof, seafloor spreading, GPS, etc. So what's causing all of that? Okay, we know plates move around. Well, why? What's the driving mechanism behind plate tectonics? What's pushing everything around? What's moving everything around? That's what we're going to explore. So, plate tectonics, as it's defined, is the movement and interaction of large fragments and a number of small pieces of Earth's lithosphere, just a fancy word for crust. Lithos, Greek for stone, sphere for sphere. Again, just a fancy term for the crust. So these are just some boundaries that show some of the plates, not all, but some of the plates of Earth. We have large plates like the Pacific plate here, the North American plate, which most of North America sits on. But we also have smaller plates dotted around the Earth as well. For instance, the Juan de Fuca right here, and many other smaller ones. So we have both large and small. So, again, there's evidence that plates move in the past and currently. But how do they move and why do they move? Well, in physics, we know that movement is caused by a force. So something is forcing these plates to move around. Well, in physics, a force is caused by an interaction. So something is interacting with the crust, the lithosphere, to break and move these plates around. And, well, what's in contact with the crust? Is it the air, the atmosphere, the water? Probably not. So instead of focusing on what's above the surface, maybe we look at what's below the surface. So maybe we need to focus on the mantle, which is interacting with the lithosphere, the crust. Now, to imagine how and why the crust moves around, I want you to think of a lava lamp. Does anybody have a lava lamp, or maybe you did at one point? A lava lamp. So the way a lava lamp works is the following. So you have some sort of light source, which produces heat. That heat heats up the material in the lamp, the lava. That hot material will rise. As that material cools down, it sinks. It has to deal with density. For instance, hot air, like a hot air balloon. Well, why does a hot air balloon rise? Because the air in the balloon is hotter than the surrounding air. So hot air is less dense, so it begins to rise. If you don't heat up that air, it cools down, cold air sinks. So that's how a hot air balloon works. If you have the burners going, it's heating up the air, your balloon's going to rise. If you take your hand off the burner and the air in the balloon begins to cool down, well, that cool air condenses, becomes more dense, and will begin to sink. Same thing, kind of a principle in a lava lamp. So why am I talking about this? Because this is a good example of something called mantle convection. Mantle convection. So it's the same process of what's going on in the Earth. So use this kind of as a mental model. So again, with a lava lamp, you have some sort of heat source, in this case a light bulb, an old school light bulb, incandescent light bulb. If this was an LED light bulb, LEDs don't really give off heat like the older filament style light bulbs. So you need one of those old school hot light bulbs. So it provides heat. That heat heats up the material in the lava lamp, so it becomes less dense, it begins to rise, and as it gets further away from the heat source, it cools down, and as it cools down, it sinks. This forms something called a convection cell, and it's a model of something called, again, mantle convection. Let me put some gloves on, and let me see if what we got going on here. I have a lava lamp. It's just a little warm, so let me see here. If we can blow me up. Hello! Okay, so you can see the hot material rising. As it gets further away from that heat source, it begins to cool down, and what happens when it cools down? It begins to sink. And that process starts all over again. As it gets closer back down to the bottom of the lava lamp, that heat source, it heats up. And what does that heated material want to do? That heated material wants to... It's going to do it. There it goes. It's almost there. Come on. You can do it. You can do it. Do it. There you go. All right. So when you you think about the workings inside the Earth, I want you to think of a lava lamp. So just like, make me little. So just like a lava lamp, same thing inside the Earth. There's some sort of heat source, all right? As you get further into the Earth, it gets hotter and hotter and hotter. So the core is going to be the hottest part of the Earth. So you got this hot core heating up the material inside the Earth. Some of that material is able to move. Remember, you have the solid inner core. You have the liquid outer core. The mostly solid mantle, but that mantle, again, it's a kind of a mix of hot Play-Doh. Think hot Play-Doh and rocks mixed together, so it can still move. It can still flow a little bit, but very slowly. And then you have that solid crust. So this process is happening in the mantle because the mantle is interacting with the crust. So the heat from the outer core and inner core reaches the mantle. That mantle material closest to the center of the Earth begins to be heated up. It will slowly move and rise. As it gets further away from that heat source, the core, it cools down and it will sink. And that process happens over and over again. Again, that's called convection. Same thing happens if you're boiling a pot of water. Are you boiling a pot of water to make some delicious macaroni and cheese? That heat source, hot water rises. As it gets further away from the heat source, it cools down, and the process starts all over again. So that's called a rolling boil. That's why it's called a rolling boil, if any of you cook. But in any case, how does that look inside the Earth? Well, it's kind of the same process. So you have that core heat source, that hot mantle material rises. It moves. It can move. Remember, hot Play-Doh, sticky, full of rocks. So it's not that it flows around like water or like the lava lamp per se, but it does move very slowly. So you get this hot mantle material rising, and as it gets further away from the heat source, it cools down. Now it's going to interact with that crust over top. Remember, it's hot, sticky material, and it will grab onto that crust and pull it apart, or in some places crash it together. And as that mantle material cools down, it will begin to sink, and that process starts all over again. So again, hot mantle material grabbing onto this material, pulling this stuff apart, so creating, for instance, this divergent boundary along this mid-ocean ridge, and that material falling back down. So it's mantle convection driven by the heat source within the Earth that causes plate movement. There you go, mantle convection. So what's causing all that heat? Okay, I get it. It's hot down in the Earth. Well, what's causing it to be so hot? Well, there's actually three main sources. Well, two main ones and kind of a third minor one. So the three main sources, number one, there's still heat left over from when the planet formed and accreted, which has not yet been lost. That's how much energy was in the formation of Earth. Can you believe it? Sorry for the little pause. There was a malfunction. But in any case, why is the Earth so hot on the inside? Number one, again, heat left over from when the planet formed. Remember that material crashing together, coming together to eventually form the Earth. Well, that crashing together, when you crash stuff together, you generate a lot of energy, a lot of heat. So there was so much of that going on, even 4+ billion years ago, 4.54 billion years ago, there's still heat left over. So that's why the inside, part of the reason the inside of the Earth is so hot, that leftover heat. That's number one. Number two, heat from the decay of radioactive elements. Now, the Earth is just a big mix of all kinds of stuff. If you've ever taken a chemistry class, the periodic table of elements, most of those elements are naturally found on Earth. Some of them are radioactive. Radioactive material, what it does, it decays. As it decays, it breaks down, but also gives off energy, some of that energy in the form of heat. So as radioactive elements are decaying inside the Earth, that's also providing a lot of heat. Earth's a big place. You get a lot of material decaying, creating a lot of heat. So those are kind of the two main sources of heat. The third would be frictional heating caused by denser core material sinking to the center of the planet. So again, as things move around, the inner core of the Earth is spinning. The liquid outer core is also spinning. The mantle is moving. The plates of the crust are moving. So as everything is moving and grinding together, just like when you take your hands and do this, that provides a lot of heat. So that's kind of the third main source. It's kind of the least of the three. The two, I guess, main ones, leftover heat from the Earth formation, radioactive decay, and then again, this frictional heating. Everything's moving around. Everything's moving around. So the inner core is providing heat to the outer core is providing heat to the mantle, and then we have this convection process going on in the mantle, which is helping to drive plate tectonics. All right. So in summary, plate tectonics is a theory, highest level of knowing, that Earth's outer shell is divided into several plates that glide over the mantle, the rocky inner layer above the core. Again, the mantle mostly solid, but it can move a little bit. Again, think hot Play-Doh mixed with rocks. All right. Plate tectonics is a unifying theory of geology, meaning once we figured this out, which wasn't until the mid-1900s, which is less than 100 years ago, we really didn't have an explanation for a lot of things like earthquakes, volcanoes, oceans, and continents, and movement, and all this stuff. We don't really have a mechanism that was causing all that. Now we do. So plate tectonics explains all of that. Because the plate's moving, we get earthquakes. Because the plates are interacting, we get volcanoes. Because the plates move around, we can create ocean basins and continents and geologic formations like mountain ranges. If it wasn't for this, we got nothing. So, and this is less than 100 years old. It's about 70 years, only about 70 years we've known about this. So like maybe some of your grandparents or great-grandparents, they didn't know how any of this worked. Isn't that crazy? We know more about space and what's beneath our feet. Think about that. So again, this plate tectonics, this theory is developed from the 50s through the 70s, and it really wasn't solidified, again, until the 70s. So again, maybe even some of your parents, if you are a little bit older student, maybe older parents or something like that, again, they didn't know how earthquakes or volcanoes worked. What? But plate tectonics, it's the modern version of continental drift, because remember, that was Wegener's idea. Continents drift around, but he didn't have an idea of how it worked. Again, that was Wegener back in 1912. He didn't have that explanation, but we do now. And the driving force behind plate tectonics is obviously mantle convection. The hot mantle material closest to the core will rise. It'll grab onto those overlying crust, that overlying lithosphere, and kind of pull it apart or crash it together in certain areas, depending on which way the convection is going. And then that mantle material, as it's further away from the heat source, the core, cools down, and that process starts all over again. Convection drives plate tectonics through, again, pulling and spreading of continents at mid-ocean ridges and other rift areas, divergent boundaries, and pushing and crashing together in downward sinking plates at subduction zones, convergent boundaries. All kinds of fun stuff. All right, so that's the driving mechanism behind plate tectonics, mantle convection. Again, lava lamp, think of that as a model of how it works. So we're going to go ahead and pause here. When we come back, we'll talk about those different plate boundaries that I had mentioned, divergent boundaries, convergent boundaries, and possible others. I'll see you back here in just a second.